Now, the last thing we wanted to talk about in this introductory video to discrete calculus, the recurrence relation. Let's say that we have a series that is, or a sequence that is defined as a a number multiplied by the previous number. We will get that we can see that a recurrence relation like this can be thought of as un equals some initial condition multiplied by a to the n, because if we introduce u2 will be u0 multiplied by a squared, or u0 multiplied by a to the 1 power and a. u0 multiplied by a1 can be thought of as u1 multiplied by a is u2. So this is the current relation. This is the recurrence relation. If we take u3, u3 will be u0 a cubed, which can be thought of as u0 a squared multiplied by a. We can see that u0 a squared is a is u2 multiplied by a. So we have un plus 1 equals to a multiplied by un. How to solve this recurrence relation is that we can introduce the un plus 1 here can be thought of as eun, and if we get this term to the left side, we'll get minus a un. We can take un as a common factor. E minus a multiplied by un equals to 0. Okay, in order to solve it, we will have un equals to u0 multiplied by a to the n. A here because e minus I is 0. E minus a equals 0. So e equals a. So the next number is a multiplied by the previous number. This is how we solve it. We will take a look at an example that is very famous to our, which is the Fibonacci series. The Fibonacci series here, which is introduced by the first two terms is 0 and 1. Then we have 1, which is the summation of the previous two terms. 0 plus 1 equal 1, so we get 1. To get this number, we sum we add the previous two numbers, which is 1 plus 1 equals 2. 3, we get 2 plus 1 is 3. Here we get 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 equals 13, and so on. This recurrence relation can be thought of as e squared multiplied by un equals eun plus un. This is derived from un plus 2 is un plus 1 minus un. We have two initial conditions is in here because we have as sort of as a second derivative, because we have e squared. So as a differential equation, recurrence relation is like differential equations. It will it will need two conditions to apply here, which is u0. The first term, the zeroth term is 0 and the first term is 1. We can get e squared minus e minus 1 as a common factor multiplied by un equal to 0. We can factor out this equation to be e minus phi and e minus psi. Phi is 1 over 2 plus square root of 5 over 2. Psi is 1 over 2 minus square root 5 over 2. This could be used from factorization. From this we can take that un is equal to some constant c1 multiplied by phi to the n plus c2 multiplied by psi to the n. You can see that this is like the previous one when we introduced that e minus a multiplied by un equals to 0, then e minus a equals 0, e equal a, then we get the general solution for this recurrence relation. Un equals some constant u0 multiplied by a, which is e equals a, so we get a to the n. N represents the nth term in the series. Likewise, we can see here we did the same thing, c1 multiplied by phi, which is the first solution of the equation, to the n, plus c2 multiplied by psi to the n. Why we get this combination together? We get this term plus this term because if this term satisfies the solution and this term satisfies the solution, the summation of them satisfies also the solution. Likewise, if we have three solutions, we will get plus c3 multiplied by the third solution, which can be thought of as zeta to the n. But we have two solutions in here, so we will not consider the third solution. If we want to know these two constants, we will apply the conditions. The first condition says that u of 0 equals 0, which can be thought of as c1 multiplied by phi to the 0 plus c2 multiplied by psi to the 0 equals to c1 plus c2 equals 0. This means that c2 equals negative c1, which means we can replace this by negative c1, which we can take c1 as a common factor, and we will left with phi to the n minus psi to the n. If we apply the second boundary conditions with the second condition, u1 equals to c1 multiplied by phi to the 1 minus psi to the 1 equals 1 from the second condition. So after a little bit of simplifications, we will get c1 equals 1 over square root of 5. So we will get the final result of un equals phi to the n minus psi to the n over square root 5. Notice that this equation is very helpful because it allows us to compute the nth Fibonacci number a lot easier than the programming algorithms which need to follow each term by term. If we go out here to the Excel, I have made an Excel to introduce the Fibonacci series here 0 and 1, 0 1 2 3 4 5 6. This is the index of the term in the Fibonacci number in the Fibonacci series, and this is the Fibonacci series. The first and second term is 0 and 1. The third term here is these two terms added together, while this is these two terms added together, and so on. We'll get 1 1 2 3 5 and so on. The limitation of this method is that in order to compute the the hundredth Fibonacci number, we will need to compute all the 99 Fibonacci numbers introduced before. But if we used our formula here, I put it in the Excel, and here it depends only on the n, on the number here. It will compute the nth Fibonacci number very fast compared to the algorithm, uh, the if we here we computed the 100th Fibonacci series and it looks like this. Here we and the 150th Fibonacci series like this. In order to see what is the power of this, we can compute the 500th Fibonacci series in less than a second. It doesn't take any time, and we can here put any nth number like the 400th Fibonacci number, and it is computed instantaneously. This is the power of formulas for Fibonacci numbers. Like 600, we need only this. We need only to increase the size of the cell because we run out of the space. This is the power of formulas in Fibonacci numbers and the power of discrete calculus.